Hello everyone. Today our team will present our project on developing a biomedical retrieval augmented generation system. Biomedical text is complex, specialized, and rapidly expanding. Traditional language models often generate answers that sound correct but lack factual grounding. To address this, we developed a RAG pipeline that retrieves relevant biomedical literature before generating the final answer. RAG strengthens answer reliability by combining two key components, retrieval and generation. Instead of relying on model memory, the system first retrieves real PubMed passages, ensuring that each answer is supported by specific context. We use the PubMed QA dataset, which is nothing but public medical question answering dataset, which provides medical questions, associated biomedical context passages, and expert authored gold answers. This makes it ideal for evaluating evidence grounded medical reasoning. Our architecture consists of four stages: ingesting PubMed QA dataset, generating BioBet embeddings for all biomedical passages, using FAISS to retrieve the closet scientific evidence, and passing retrieved context to large language models to generate grounded answers. We use BioBet as our embedding model because it is trained specifically on biomedical literature. This allows our vector-based search to better understand domain-specific terminology. All BioBet embeddings are stored inside a FAISS index. This enables extremely fast similarity search across thousands of biomedical passages, ensuring both speed and accuracy in retrieval. To compare different reasoning styles, we evaluate three language models: BioGPT, FLAN-T5, and Phi2. BioGPT is specialized for biomedical text, and FLAN-T5 is strong instruction following and reasoning, and Phi2 is compact yet efficient casual model. This comparison helps us determine whether domain specific or general models perform better in RAG. Our system integrates embeddings, retrieval, prompting, and generation into a single pipeline. When a question is asked, the system retrieves the most relevant biomedical evidence, constructs a consistent prompt, and generates an answer grounded in real scientific context. Now, Muralidhar will explain the code.
Yeah, continue with the Sunana's inputs. The first thing we have to do is install the dependencies. We begin by installing essential libraries like TensorFlow datasets to load PubMed QA, transformers for loading models, the sentence transformers for embeddings, and the FAISS index for fast similarity search. And here we have installed the every library, and after that we have loaded the PubMed QA, which is the public medical question answering systems, and it contains the expert long answers. This serves as our data sets for retrieval and evaluation. Then we have prepared the records and data frame. We extract only the needed fields like the questions, passage snippets, and rolled answers, and convert them into data frames for easier processing. And then we have built a retrieval corpus. All the biomedical snippets are flattened into a single list. These passages form our searchable knowledge base. Then we generate the embeddings using the BioBet. We converted every single snippet into numerical embedding. Since BioBet is trained on biomedical text, it captures domain-specific meanings accurately. After that, we have created an FAISS index, which enables us for faster nearest neighbor search to find the most relevant biomedical passage for each question. Then comes the retrieval functions. We used a custom retrieval functions for the top k most relevant passages for any query by comparing embeddings using FAISS. And then we have loaded all the generated models, which are the BioGPT, then the FLAN-T5, and then the Phi2. And these are all this allows us to compare domain specific, the general instruction tune, and the compare models. And then we have created a custom prompt construction. This is a unified prompt template that combines the retrieval context with the question, ensuring consistent inputs across the fields. Then we have generated the answers based on all the models that we have trained on the RAG system, which is the BioGPT, FLAN-T5, and the Phi2. And then we have asked the questions to the models, and we have achieved multiple results from them. And here we can see where we can see that the BioGPT and the Phi2 will be giving us the context-based answers, whereas the FLAN T5 gives more like the yes or no answers, and limited time answers for the which it can't find in the passage. Then we have done an average over the scoring, and we can see the accuracy. Here we can see the question and how the three models perform over the question, and what's the accuracy and what's the factual accuracy. And we have given the model comparison on the PubMed QRAD. Here we can see that the BioGPT is performing well, and FLAN T5 is mostly balanced, and Phi2 lacks the factual accuracy. Spandana will continue out from here.
In our implementation, each component of the RAG system is built step by step. We begin by preparing dataset, extracting biomedical questions and their corresponding context passages. These passages are processed into retrieval corpus, embedded using BioBirth index with FAISS, and later combined with prompt templates for answer generation. This forms the foundation of our end-to-end system. We generate embeddings for every biomedical snippets using BioBirth sentence transformer model. These embeddings are stored in a FAISS L2 index, enabling fast and accurate nearest neighbor search. This ensures that for any given question, the most relevant scientific evidence is retrieved within milliseconds. Once retrieval is complete, the top passages are merged with the input question using the unified prompt template. BioGPT, FLAN-T5, and Phi2 generate answers using the same prompt structure, ensuring consistency across models. This allows us to compare different architectures fairly under identical retrieval conditions. To evaluate the generated outputs, we rely on two main key metrics. BERT score F1 measures semantic similarity between the generated answer and the reference biomedical passage. Factual accuracy score produced using a FLAN-T5 large grader, which assigns a value between 0 and 1 based on how well the answer aligns with retrieved evidence. These metrics allow a balanced assessment of quality, coherence, and actual groundings. Our results reveal clear distinctions among three models. BioGPT produced domain-accurate biomedical terminology. FLAN-T5 achieves the highest factual grounding and coherence, while Phi2 performs efficiently given its small size but still trails the other two models overall. The comparison chart visualizes these differences across metrics. In conclusion, our project demonstrates a complete biomedical RAG pipeline that integrates dataset processing, scientific retrieval, prompt engineering, and multimodal evaluation. The result emphasizes the importance of grounding large language models in retrieval evidence, especially in specified fields like medicine. These pipelines can be expanded with larger datasets, improved retrievers, and more advanced models, making it a strong starting point for future biomedical AI research. Coming to the references, this slide lists a key academic references that supports our project. These sources provided essential insights into our RAG architectures, language models, and the methods we used. Including these citations ensure academic integrity and acknowledges the foundational work behind our study. Thank you, and we welcome any questions.